The normal approximation to the binomial. Because it involves combinatorial factors, the probability function for the binomial is annoying to work with. For example, in homework 2, question 14, we want to find k such that probability of x bigger than or equal to k is at least 0.95. Here, x follows the binomial distribution, n is 400, success probability 0.95. Because n is large, the expression probability of x bigger than or equal to k is so annoying that other than repeated try and error, we don't really have a better way to deal with this sum. This is why approximations are needed when n is large. There are two regimes of how the binomial distribution look like. In the first case, when n is large and p is moderate, the probability function of x can be approximated by the probability function of a normal random variable, n. The normal distribution is a continuous distribution that takes in two parameters, the mean mu and the standard deviation sigma. We will learn more about continuous distributions later in the book. For now, we think of it as a particular family of functions. To approximate binomial np, we need to set mu equals to n times p and sigma equals square root of n times p times 1 minus p. The big advantage of working with the normal distribution is that it behaves nicely with linear algebra. That is, if n has normal mu sigma distribution, then n minus a divided by b has the normal mu minus a sigma divided by b distribution. In other words, translating and scaling a normal just gives us another normal with slightly different shape. In particular, if we subtract the mean and divide by the standard deviation, then we get another random variable, z, with normal distribution, mean 0, standard deviation 1. This is called a standard normal. The probability function of a standard normal has an explicit form, and finding probability of z less than or equal to some value little z corresponds to finding the area under this curve. That is integration. The antiderivative of f is the function phi, called the standard normal CDF. The normal CDF and its inverse can be accessed in R by the command pnorm and qnorm. So in summary, after some algebra, we can compute probability of x bigger than or equal to k by turning it into a problem about probability of z bigger than or equal to some little z. That is, we simply need to evaluate the standard normal CDF. Let's look at homework 2, problem 14. In this case, we would write probability of x bigger than or equal to k is approximately probability of n bigger than or equal to k, where n is the normal mean np standard deviation square root of n times p times 1 minus p. Now we can do a little algebra. So we standardize n, subtract the mean divided by standard deviation. We do the same thing on k. And this gives us probability of z bigger than or equal to k minus mu divided sigma. We need this to be at least 0.95. So the problem becomes find z star such that probability of z bigger than or equal to z star is 0.95, where z is the standard normal. Now we rewrite in terms of the normal CDF. So z star equals phi inverse evaluated at 0.05. Plug into our inverse normal CDF calculator, and we get z star is equal to minus 1.64. Now we solve z star, which is minus 1.64, is equal to k minus mu divided by sigma. Plug in n and p, and we find k to be 372.8, which is approximately 373, as we got from try and error.